Good morning, everybody. As you can see from the slide that's up, today's presentation is sample survey, but we're going to talk about a new kind of sampling called stratified sampling. And if you want to refer to the book, chapter 3 of law is devoted to stratified sampling. What have we done so far? We have discussed different ways of drawing a sample of size n from a population of size n, which you're very familiar with. We've also discussed the different population parameters that you could estimate. You could be estimating the population's mean, or the population's total, or the proportion of the population that have a particular property, and you would estimate something, with other words, about the population. We've looked at these three parameters using your information from the sample. And then we said no matter which parameter you're working with, that's the parameter from the population values, we would say the true population value is somewhere in this interval, right? You should be very familiar with that. So we spoke about the mean, the total, and the proportion as being the possible values of theta, the population parameter. But then we also said we know that these confidence intervals and the estimates, there's not just one formula. For example, I want to estimate the population mean, and there's just one formula. It's different whether you're doing simple random sampling with replacement or whether you're doing simple random sampling without replacement. These different, that's why we had those columns, and it was one side was for with replacement, one was without. Particularly the variance formulas of the estimators, these things differ a lot between the different sampling types. So we've done each of these, mean, total, and proportion, estimating that for the two methods, simple random sampling with replacement and simple random sampling without replacement. We also discussed that the simple random sampling without replacement generally gives you better results. Now, you might recall that when you estimate the mean and the total of the population, that for simple random sampling, and if there's nothing else written, you know it means without replacement. So simple random sampling without replacement, choosing n elements from n. If you want to estimate the total, you use ny bar, and that's the formula for simple random sampling without replacement, estimating the variance. And we said this is the thing we always want to make small. Similarly, if you estimate using simple random sampling without replacement, if you estimate the population's mean, you can use the sample mean as your estimate, and this is an expression for the variance of that estimate. And we know we want the variance of the estimate, with other words, in the case of estimating the total, I want this to be as small as possible, but we also want, if I estimate the population mean, for this to be as small as possible. So why would you want that? Can you remember? Why do we want the variance to be small? You can remember. Yeah, the error is small, because if the variance, just look at the statement, you want the variance of the estimator. It means the different values the estimator can take. If your estimator can be very different, if I take this sample compared to if I take that sample, the values of the different samples, the estimates are so different, then you can imagine they can't all be good at estimating that mean. So a big variance in the estimate is a problem. So we say now, well, let's look at this formula, for example, if I'm estimating the mean. I'm estimating the population's mean. This is the formula for the variance. You can see here, I choose my sample size n. Big N is fixed because the population is fixed. Big S squared, that is the variance of the population. I can't do anything about that. If this variance is big, it must probably mean your S squared is big. And you can't change S squared, you can't change big N. But you can change little n because you're choosing the sample. So you can say, well, I don't want my variance to be big. I'll work it out and I see it is big. So the only thing you can do is to make your n, your sample size, bigger. But the problem is it's expensive. It comes at a cost. It takes more time and it costs more money to sample more farms or whatever you're sampling. So what else can we do to make this? So the question today is, What can I do to make this smaller, the variance of the estimator, if I don't want to just keep increasing the n? Because the problem is this S squared is big and it's expensive to keep increasing. Is there something else I can do? And before we go further, I'll put this little note in. The sample mean, you know, is y bar, little y bar. The population mean, I usually use a capital Y bar. But lots of notation and books often use little y bar with a U next to it. That means universal. So these two are identical for the population. So the sample mean is always little y bar. The population mean is big y bar, but at times notation is also to use another small y bar, but to put a U next to it. So just be careful. You see here, for example, I'm estimating population mean, though it's a small y bar because of the little U, so just be aware of that. Now, if, for example, you want to predict the average income of a household, S squared will be very large in South Africa. Why? S squared is the variance of the population. There's some really poor families living not even in a shack, jondolo, whatever you call it. They don't even have that. They live on the street maybe, but they're also very wealthy families. So that S squared has to be big. So that will make my estimator of the variance big. So I want to make this variance of y bar smaller because this S squared is definitely, when it comes to average income, it's going to be large, my S squared, household income. What won't be large? If I say, let me look at the variance of adult men's heights. You get some short people, some tall, but there's not as much variance between people's heights as there is between income. You get very poor people and very rich people, right? So that S squared is really big. So what can I do? I don't want to keep taking more and more big N. What can we do? The answer is stratify. It's a new concept maybe for you. Instead of just taking N elements, little n from capital N in the population, that's what we've always done. We're going to do something new. We're going to divide our population according to some criteria. And then we're going to separately select, instead of just saying, I take little n elements from the population, I'm rather going to say, I'm going to divide my population into two groups. Say, here's the group. There's some, you can't see it. Here's my group. I've got some men in blue, and that's supposed to be ladies. They look like scary men with beards. I've got ladies and men. So instead of just picking 6 people, I'm going to pick from those. I'm going to pick 3. For some reason, I want equal number of ladies and men in my sample. So I separately pick from the ladies and separately pick from the men. That's called stratification. You just divide the population into groups. What do we do? What is the basic idea? You can see here, here's my big population. N is the sum of the capital N's. So I've got first year students, second year students, third year, right up to PhD students. Can you see, for example, you could stratify all the students of this university depending what year you're in. So you've got a group. So if you want to pick 100 students, I want so many first years, so many second years. If you just pick from the big set, you can't say how many first years you want. So that's what we do, divide the population, and then we pick from the, let's think of this as first year students, second year students. If I want to pick, say, 50 students, I want 5 first years, say. These are all the first years. I put them into one group, and then I just select from the first years however many I want, little n1. So you separately, you work just with first years, you do sampling. Just like we did in the previous chapters, selecting little n from n, you use all the same theory, but you're only working in this group. Then you do it all again for this group, and so on, and then you combine it at the end. That's all it is. So you divide your population into H. We call these groups strata. 1 stratum, 2 strata. So we divide it into strata, that's the plural, of similar items, similar in some sense, like everybody's first year here. Everybody, it could be all the males there, all the females, whatever the story is. But what's important is you sample independently. It's not like if I take a man here, I make sure I take his wife in the second group. The two mustn't have anything. You sample only from this group, and then you sample from the other group. So here's your population. The entire population for the whole everybody together. You're obviously, there's so many in group 1, so many in group 2, up to so many in group H. So the whole population, big N, is still how many are there all together. Your little n is how many did I choose all together. I chose N1 from there, N2 from there, so that makes sense, right? So there's nothing difficult about that. Now, what is the basic idea? You calculate a stratum estimate. Just like we did before, we choose little n from big N, but now we choose little n1 from big N1. We actually ignore all this. We only work with the first stratum, as if it's the previous chapter. Then we do it again for this one. Then we do it again for each one. We calculate a stratum estimate for every stratum. Then we combine them together. We've got an estimate for this group, an estimate for that group. Say if I want the mean, I can have every group's mean, and then I must just put them together to get the population mean. It's really very simple. But what's important is this last one. Sample independently. You don't look at one group and then attach. What you do in group 1 must have nothing to do with what you do in group 2. And the beauty is you can then just add the variances together. You know, variance of A plus B is variance of A plus variance of B as long as they're independent. So let's have some examples. The first example is, I wish to determine the average amount spent on groceries by household of a particular geographic area in South Africa. Let's say the whole KZN. I want to know what is the average amount a family spends on household, spent on groceries by a family. What's wrong with that sentence? I can tell you straight away. I wrote it last night. You know what? I should have said, how much do you spend on groceries? I can't even tell you because you haven't said a day, a month, a week. So I better put it in there. Can you see that? I wish to determine the average spent on groceries. Should it be a week, month? I didn't say. So that's a nonsense question, but never mind, you get the story. So I want to know the average. Now you can imagine that if I had for the whole KZN, as I said, you get very poor people, you get very rich people. So it's going to have a big S squared. So classify, so what I'm going to do is I'm going to make 2 groups. And I'm going to say rural people and urban people. People that live in the rural area and people that live in the city area. If you live in a rural area, you might have a farm and you've got subsistence farming, you've got your own chickens and you grow some sweet potatoes, whatever. So your expenditure, you also live far from the city, so you don't spend as much on household because you can do your own stuff. And also there are more poor people in the rural area. So I divide them like that because spending will be different in rural compared to urban. When you divide, that's the important thing. You must divide the 2 groups so that these are more similar and these are more similar, but they're not, if I put them together, they're quite different. For example, if I'm looking at household expenditure, I would think rural and urban would be different. That's why I make that what we call the stratification variable. The variable how to stratify says, where do you live? Urban or rural? I wouldn't say, are you tall or are you short? Short people don't spend less money than tall people. So you wouldn't say your height, I'm going to classify into tall people and short people. That wouldn't make any sense. So my S squared could still be big. So you're picking from each group, right? And I've said it there. My classification variable to make the strata is where are you located, your household? Are you rural or urban? There will be some rural people that spend a lot on household maybe. And there'll be some urban people that don't spend a lot. They live in the city, but they're poor. But bottom line is, if I put them together, there'll be a bigger variance than there is now. Another example, another reason to do stratification, you can become more representative. And if you read the story, it comes straight from law. What they're saying is, suppose that you've got 1,000 males and 1,000 female students, and you want to choose 100. You want roughly equal males and female in your sample. But if you just choose 100 from the 2,000, you could get 70 males and 30 females, or the other way around. So it is a way of controlling. It's called proportional sampling. So stratification, if you first divide it into male-female, you can make sure that you get good representation. And sometimes you say, the males don't differ so much, I'll just take 30 there and I'll take 80 there. It doesn't mean you have to take the same proportion. You can, depending on how you're making your sample. So the third example is to draw a sample to find the average blood pressure for citizens of Durban. I want to find out what's the blood pressure in Durban, and I want to find out what's the blood pressure in China, say in Kyoto, Japan, because those people, maybe they do like exercises to stay calm, and if you're under stress, your blood pressure goes up. So we want to work out, there's somebody that wants to work out the average blood pressure. So they would take a sample from here and a sample from there to compare them. But it's a medical fact, you might not know it. Persons of different ages tend to have different blood pressures. Children usually have lower blood pressure than old people. Because blood pressure is one of the variable of interest, the data, the Y, in this case will be, I select a person, I measure his blood pressure, I record the blood pressure. So the variable of interest is blood pressure, but what makes the blood pressure vary a lot? Age, across age. So that is why we would stratify to represent the age group. Say we'll have one group for everybody over 60 as a stratum, another stratum for people between 30 and 59, whatever. But you'll get your S squared down, your Y values, how they vary, as long as you use age to stratify. So let's now get to the notation. You understand the basic idea of what we're trying to do. You've got a big population with N values, and I divide them into groups depending on age or gender or whatever, or rural, urban, whatever the story is and the data looks like. And you need to think about which groups vary within themselves less than across. If I, for example, want to know how much money do you spend on clothes, okay? What would be my stratification variable? Definitely gender. I think men spend less, right, than women. Also, whether your income. If I have people's income, if you're working, people that earn more maybe spend more on clothes, I don't know. But suppose a population, now this is the notation, so this is just the mathematical notation. You need to know it because we're going to give you formulas, and if you don't know the notation, you're not going to understand it. So we've got a population of size big N, and it's been divided into 8 strata. There it is. N is N1 plus N2 plus big NH. So that we know for any stratum, say stratum L. Stratum L here is just a general stratum. Say like L is 2 will be this group. Okay? YRL is the ith observation of stratum L. So for this first one, it will be Y11, Y12, Y13 up to Y1N1, big N1, okay, because they're N1 elements. So we're just naming each one depending where it is, and it doesn't matter whether you swap the R and the L around, as long as you're consistent. Big NL is obviously, big N2 is how many are in stratum 2, little NL is how many you chose, it's obvious. What is TL? You can see here. Sum from Rs 1 to NL, this is for stratum L, so you're summing all the elements of that stratum, can you see? And that's obviously going to give you TL. T1 will be Y11, Y12, plus up to Y1, big N1. It's obvious from the notation. The 8 strata, so I've just taken a general one, so I took H from one of those, and for that notation, the elements look like this. Obviously, I'm just spelling it out again. The total for that stratum, if it's stratum 8, you would just add together all of them. It's exactly like the previous chapter, but we haven't got one population and one sample. We've got a slither of the population. And the mean is as normal. If those are the elements, how would you find the mean? Obviously, like that. And the variance, S squared H, is that. The point is you want this to be small as possible because your S squared is big. Everybody together, first year, second year, up to PhD students together, vary a lot. But if I just look at first years, maybe they vary less. So you're trying to make these values for the different strata small. So that is why you look at your stratification variable. And what are we wanting to estimate? We're going to do this breaking up. We want to estimate T, Y bar, and P. Just like before, but using stratification. We're also going to do it for simple random sampling with replacement, as well as simple random sampling without replacement. The beauty is that because we've done all this work already, we can actually very quickly get to these results because it's just adding together what we know from the previous chapters. So stratified sampling is now we're going to estimate the total, and we're just going to add together the estimates for each stratum. So just like we did in the previous chapter, you're only going to work with this one, work out the mean or whatever total. Then you do it for that one, and then so on, and you combine them. And this is how you do it. If you know how to estimate the total, because if we ignore all this, we only look at this one. If you're picking little n1 from big N1, we're only working in this stratum, you know exactly how to estimate the mean because it's our previous chapter. But you do it for each stratum separately. And you can estimate, in this case, the total for that. You estimate the total there, using the previous chapter's theory. And then this says if you want the total overall, you just add the totals together. Isn't that obvious? If you know how to work out the total for this group, and you know how to estimate the total for that group, for each group. If you want to estimate the total spent on groceries by all rural people and all urban people, then if you know how much the urban people spend and you know how much the rural people spend, just add them together. So it'll tell you. So that is obvious. But now if you take the variance of this, imagine from all your knowledge you've got about earlier years, the variance of t hat is just the variance of this here. It's the variance of the sum. Okay, so I want the variance of t hat, which is the variance here, which is the variance of that. But remember, I said the key thing is we work independently between strata. So that's what makes it so easy. The variance of this is just the sum of the variances because of the independence between strata. And that's an important point. So this is what we're going to use throughout. We're going to use all our previous theory because each of these will just be as in chapter 2. We're using simple random sampling. So sampling is conducted independently in each stratum, and that is why we can just add the variance of the population, add the individual strata variances as discussed. Now, recall simple random sampling without replacement, with no stratification. I'm just going to keep going, just so that you know, because I want to do this in one video, and I'm going to put the videos up this week, so that you can look at all the previous videos. The PowerPoints I've been putting up, but not the videos. At the end of this lecture, I'll put up the previous videos so you can look at them when you're learning for the test. So what we're trying to estimate now, simple random sampling without replacement, with no stratification. This is now from chapter 2. We want to estimate the total. You know the total is NY bar. This is nothing to do with stratification, no stratification. What did we say previously? This is how you do it. I had another column if you're using with replacement, but today I'm doing without replacement. And we know S squared is for the whole population because it's the variance, but when I start estimating the variance, because I can't work out the S squared, you're going to have a little S squared, and that's what S squared is. Okay? So that's very simple. Now, we want to do simple random sampling without replacement, where we're estimating the population total with no stratification, and that's what I've just shown you. And then I'm going to do it with stratification. So if you go back to the previous page, this here is simple random sampling without replacement, no stratification. I'm going to put that on one slide now, these exact results using this information, but I'm going to put below it, if you stratified, what you get. So simple random sampling without replacement. I want to estimate my theta I'm interested in as T, population total, without stratification. That's like the previous one. The previous chapter, you didn't stratify, and then I'm going to do it if you do stratify. Okay? And you'll see how simple it is. You know from before, from chapter 2, when you wrote your last test, how do you estimate the total? You take the sample mean and you multiply by how many persons in your population. And it looks like that. Okay? The variance is 1 over n, 1 minus n over n s squared, but the n comes in, so that gives you the variance is n squared. This comes exactly from the previous slide. There's nothing new about that. Then, your s squared, I've just put it there for completeness. Now comes the new part. If you're doing it with stratification, now if you go back 2 slides, you'll see I said t hat is always given by sigma th. It's obvious. If you want to know what's the overall total, you want to know the total here plus the total there and so on. Isn't that obvious? But t hat h is exactly like here. Because what is t hat h? I'm estimating the total of stratum h. Now each stratum is like a population on its own. And you know if you want to take n from n, you estimate the total by ny bar. But now I'm taking n1 from n1, n2 from n2. So if I'm just working with stratum h, it's exactly like this. I took little nh from big NH in stratum h. So it's just the t hat h is exactly like that, but I'm working in stratum h. Can you see that? It's identical. So all you have to know is that, and you'll be able to write that down. Because it's sum from h is 1 to h, and now you're just treating your population as stratum h. It's not a population where you're taking n from n, you're taking nh from big NH. So it's exactly like that, but you're working in stratum h, and then you add them together. So it's very simple. And your s squared look like that. Guess what? S squared h is the same, but they're just h's everywhere because you're in stratum h. So you're independently working in each group as if that's your population. Do you understand? And then the variance, similarly, we said the variance is the sum of the variances. If you go back 2 slides, when you stratify, because of the independence, remember I said, the variance over all, t hat is just the sum of the t's. So the variance here is the sum of the variances. But each of these variances are exactly like that, but they've got h's everywhere. Because you're just working in stratum h. And then you sum through the variances. Can you see that? I think it's something you just got to sit with. It's really not hard. Now, what is the gain in effort? Stratification, if you first put people into group and you separately from each group sample, it's a little bit more effort than just taking the whole group together because you first have to separate them. Why is it better? If you're doing simple random sampling without replacement, with 8 strata, here, this is the variance of your t hat, your total. The same variance, if you don't stratify, looks like this. This is the formula if you go back to the previous page. This is, so we're really saying we're comparing this and this. Okay? If we compare these two, look at this. This will be everybody in one population, not didn't stratify. It's like the poor people and the wealthy people are all rural, urban, everybody's in one big S square. Whereas here, you've separated out. Let's put all the urban people together and all the rural in S2. Or you've got the blood pressure of all the young people, the babies and the little kids, the blood pressure of the old people separately. So these S squared is the variance of group 2, say, if you've got younger people, older people, and so on. So this is definitely going to be smaller values than these. And that's why this variance will generally be smaller than that. And that's why when you stratify, you must look at what you're measuring and say, let me stratify so that the groups are different. All the old people together, they're very different to the young people. So that these S squareds within themselves are as small as possible. Because there's big variance, so you put all the ones that are similar into one stratum to make these things small. So that is the difference, because remember I started off by saying, if this is big, the only thing I can do is make this big to help me make the variance small. But the other thing you can do is to, if you're looking at this formula, you can say, if I can stratify and put all the similar people together, then I can make these things small, and then sample from each similar group a certain number. I can make this will become smaller, and that will make that small, without having to make your n bigger. Okay, So hopefully that's clear to you. So we're exploiting the fact that the variable of interest, the Y values, the blood pressure, whatever, is going to vary less within strata. These S squared L's will be smaller than across the whole population here. That is, we choose a stratification variable so that these S squared L values vary less than this S squared. Hope that's clear. The next thing I've done is to put together for this particular case that we've been studying, simple random sampling without replacement, sampling from the whole population without stratifying and then stratifying, and I've estimated the total, the variance, and then estimating the variance, just so that it looks similar to what you did before. You're used to the NY bar, that comes from what you did before, and here you're just summing it together. Similarly, you're used to that one, it comes from your previous chapter, and this is already all developed in the previous slides. It's just that I thought I'd put it into a table for you so that you can more easily look at it. I'm not going to, in the test or exams, give you this. You should be able to take this and know from the previous slide that you just sum them together. Okay, so these things you must be able to do yourself. And here I've put in as well the estimated total. It's just the sum of the THs. You can see here, TH is sum as if you're sampling from each stratum. So you're going to sum, and then you take this value and just put H's. Similarly, the variance of this is the variance of each of these because of independence. So you're just going to go NH squared, and all of this you're just summing together. So you should be able to do that. The next example is one where we discuss law, page 75, the example we've done so often. We have 3078 counties in the USA. We sample 300, and we've got information on how much of each county is under farmland, and they want to know the total or the average or whatever, depending on the story. So in this particular example, this is what the original data looked like. You can't really see, but they've got, for example, Coffee County, 175,209 acres are, I think it's millions of acres or thousands of acres are under farmland. And for each of these. So this is this is county number 1, county number 2, and this last one would be county number 3078. So that's their whole list. And this is how many acres. Can you see there's some big values, 175,209, and then there's some smaller ones, this is only 57, and so on and so on. Can you see that? Now you can't just say you've got all your population values, let me take all the Y values and put the big ones together, because you don't normally have all the Y values. So this is just a demonstration data. So they've got 3078 counties, and what they did, they divided them into 4 strata. So instead of just taking 300 from 3078, they said, let's divide it into 4 groups. Do you know how they divided them? They said, depending where the group is. So you can see the groups here. Some are on the northeast of the one stratum. You see the word stratum. Northeast, the north central, the south, and the west of America. So they said there are 220 number of counties in the stratum. So there are 3078 altogether. If I divide the America into these 4 areas, there are 220 counties in the northeast and so on, 422 in the west, and if I add it together, I get 3078. So what does that mean? They took every one of these 3078 counties and they put them into one of these 4 groups. Can you see that? This is the number they sampled. There are 220 in the northeast. The number they sampled is 21. They're 1054 in North Central, and they sampled 103. If you add this together, they're 300. Can you see that in the previous chapter 2 of law, they had 3078 counties, they sampled 300. They've still got 3078, and they've still sampled 300. But they didn't just pick any 300. They picked 21 out of 220. 103 out of roughly 10%. Not really, they should have taken 22 for some reason. It varied. They wanted to maybe take 22 and the one didn't get data, but they tried to take roughly 10%. Can you see? So this is the same idea, still 300 from 3078, but first dividing into strata. And I've put that little picture up so that you can remember what we're doing, and just so that you're sure of the notation. Big N2, this is N1, N2 is 1054, little N3, I just grabbed one, will be 135, and so on. Big N is how many there are, little n is 300. So it's the same picture, just showing you the notation. So what we did here, we've got a sample of 300 from the population of 3078, but we're using simple random sampling, with other words, without replacement, if we don't say with replacement, and we did it from a population of 3078 counties. So there it is again, and then I just put big N1, little n1 in case you're confused, which I'm sure you're not. Then they did this, which you didn't have before. What they said, just for interest, in the northeast, we know the 21 we chose, but out of those 21, what is the average size? There it is, 97,629.8. I think it was thousands of or millions of acres. I think it's thousands of acres of farmland. In the north central, it's 300. Can you see the numbers get bigger as you go down? So what it means, in the west, there's far more land that is under farming than in the northeast. Can you see it? So these 41 varied a lot more. You can see it. Look at the variance. Look how big the variance is here compared to that, And the farms were much smaller in the northeast. There were 21 of them, and that's the average size. If I put them all together, the variance would be way, way bigger than this biggest number. So I've just put some values. This is S1 squared, just so that you... So note how the average number of acres under farmland differs between the strata, with the first strata northeast having smaller number of acres under farming per country than the last. Far average smaller here than here. Okay? So that's what made us think to do this. Now, this looks complicated, but it's actually not. I've just in the previous table shown you this is how we use the variance formula. Okay? How do we work out the formula for the variance? Now you can see here, we'd have to go back to the previous slide. You can see here, we know we chose 300. This is little n1, that's big N1. This is S1 squared. This is y bar 1. And now I'm really just going back to this. Let me just go back. I'm just doing stratified. I want to estimate, if you want to estimate the total, I'm going to do it like that. You want to estimate the variance, I've got to do it like that. Okay? So let's just get back to that page. Here, the variance of t hat 1 is n1 squared, right? There were 220 in the first stratum in the northeast, and I chose 21. So 220 squared, 1 minus 21, S1 squared, I've just shown you on the previous page. Here's, you know there were 220, little n1 is 21, this is your S1 squared, so it really is just a case of substituting in, and you work this out. So this here is n1 squared, 1 minus n1 over big N1, S1 squared. It's this thing, just for L equal to 1. Can you see it? So I want to work this out to estimate the variance. So I'm going to work it out for L is 1. Here I'm doing it. So it's just L is 1 everywhere. I do it here. That's the answer. And that's why I put it here. So for the northeast, this is the estimated variance of the total farmland under, total acres under farmland for this northeast. Similarly, you can do everything the same, but you'll have 2's everywhere, and you'll get for north central that and that and that. Then if you add them together, because look what this says, to get the variance, you must add the variance of each stratum. If you add them together, it's this. So obviously, that's the estimated variance of everything. So you can see here then, that's the estimated total. Similarly, we know this is the total for northeast. This is the total under farmland for central. The overall total is the sum of the different totals for each stratum. This is a total for stratum 1, total for stratum 2. So this must be T hat. It's straight from those formulas. It looks complicated, but really it isn't. So that in the end, we can want to compare now the results we obtain when using stratification and when not, when using simple random sampling without replacement, both when stratifying and when not stratifying. Before we go further, I want to make you remember something that you should know from first year, but from our experience, students often don't know this. You know the box whisker plot, right? If they're outliers, which means they're more than 1.5 times the length of the box above the top in the third quartile, but outliers just means the values that are too big or too small, we ignore them. So we've got the smallest value that's in our study and the maximum value, because we've left outliers. There's a formula to work out the outliers. So now we say there's a lowest value, there's a quartile, which you all know means 25% of all values are smaller than that. The median is Q2, 50% of all the values are smaller than that. You know the Q3, 75% and so on. But you must probably have not ever really, so you're all very familiar with that. And this is because I want to show you a graph. And if you don't have a good understanding, it's going to be a problem. What I found the easiest is to say that's my minimum value. That's Q1, right? That's the median, Q3 and the total. 25% must lie there. 50% is below the median. But if 50% is there, and I know 25% is there, it means 25% is there. Similarly, 25% is there because there's 3/4 under and there's 25% there. What a lot of people don't think of, what it really means, there's 25% of my data there, 25% there, 25% there, and 25% there. So if you put all your data in a row on a line, maybe there's some with equal numbers, you're cutting your data in 4 equal places, but not equal length there. It means if there are 30 data pieces there has to be 30 there as well. Suppose I've got 400 data pieces. There has to be 100 below the quartile. There has to be another 100 there has to be 100 there, and there has to be 100 there. You're cutting it so the equal number of data pieces. And if that idea and that concept is clear in your head, then only will you understand the next picture. So what this is about, we're discussing now, so remember this picture in your head. Equally many pieces of data in each of these 4 groups. So we're now going to look at not stratifying and taking 300 from 3078 and you stratify. The way we stratified, we said the 220, we took 21 from the northeast and so on, you get it? And then we know we got this story, we've already gone through that. But what we're interested in is actually saying we see it differs a lot here. There's smaller farming areas in the northeast and in west and so on. So here now is northeast, south region, north, central, west. What they did here, they did a box plot for all the farms in the northeast. The median, and I made it with color, the median is the purple. So let's just look at northeast. How many were there? 220. There were 220 farms, I sampled 21. What they're saying, in each of these, remember, if you look at, there must be as many values here between the maximum value in the top of the box. There are as many values there as there are between the middle line, which is the median, and the top of the box, as there is between the bottom of the box and the middle line, and so on. Those are your 4 areas. You can see here. Can you see here? Then say there are 20 farms there. Let's say there are 100 there. There must be 100 there. There must be 100 there. There must be 100 there. So you can see these are very similar. There are just as many farms sizes here as there is there. So they're much more spread out at the top. If there's like a 60, there could be a 65. Whereas here, there could be many 42s, whatever. So you can see that's how you must view it. Where the lines are close together, because that's Q1, Q2, Q3, Q4. So you must always think of it as similar. But in any case, just focusing on the median, 50% of the farms in the northeast are below this value. 50% of the farms in the south are below whatever that reading is. Can you see the medians going up, up, up? So it shows, and you can see, look at the spread here, there's a lot of spread there. So now we suspect that because all this, how did we stratify? We stratified by north, east, south, north, central, west, where they are. Does it make sense? Yes, because these farms are definitely smaller than these. So by stratifying like that, I suspect it will give me better results than when I just took 300 from 3078 without stratifying. But how much better? This is actually the table you get. If you don't stratify, that's chapter 2. We estimated the total to be this. But if I do stratify into those four areas, this is it. You get this. And if you go back now to that table that I had with lots of writing, you'll see that you get this. So what it means, the T-hat, the estimate, both times I did simple random sampling, without replacement. Here I took 300 values from 3078 without stratifying, and I got that estimated total. Same data set, when you stratify into those 4 areas, it's quite different. Now somebody says, which one of the two do you think? Now you've got to say, I've got 2 answers for total estimate. Which one would I rely on more? Which one is the more reliable one? All you have to do is look at the variance. The one with the smaller variance is always going to be the better one. Look at the variance here, 3.3, 2.54. Definitely, I would say that's closer to the real value. Because between samples, it differs less. Very important, if you're given a number of estimates, which one is the most reliable? Look at the corresponding variance. So this one, I would go with that. So the estimate of T differs. Okay, which one is better? And I've put here the lower variance is here by stratification. So that is the ideal one. But now we're saying, now if you look at the previous one, you get that variance. If you stratify, that variance. If you don't stratify, and if I take it as a ratio, the variance when you stratify, estimated for T-hat, divided by the variance estimated for T-hat when you don't stratify, it's 0.75. What it means, we actually reduce the variance by 25%. So what it's saying, if you've got 300 from 3078 and you don't stratify, it's the same as taking 225 when you stratify. Now there's a cost. You've got to go to the farmer, measure the land, whatever they do, and make sure that it's true what he's saying. But you can actually, can you see that selecting 300 when you don't stratify for this example is the same as if you didn't stratify, as if you stratify and you just go to 225. So it's much cheaper. You can make your N. Remember I said you get better results if you make your N bigger. Here you can get better results by making your N smaller because you stratify. So it's not generally true that you get 25% reduction always. Just with this example's data, the reduction was 25%. Now, ideally we should have a rest, but I'll just keep going so that we can finish a little bit earlier. Let's estimate the population mean now using simple random sampling without replacement and stratification. What we did before is we looked at the population total. So just like we did, remember I said the theta we're interested in is T, Y bar, and P. We've already done T, now we're doing the mean. So it's everything the same idea. So suppose we're interested in stratifying, and as before, we've divided into 8 strata, and we're now going to do simple random sampling without replacement again, but we're not estimating the total, we're estimating the mean. So in this case, the theta we're interested in is Y bar, and we can have simple random sampling without replacement as we had before. This you're already aware of. This is from the previous chapter. I want to estimate the population mean. I know I use my sample mean. I want to estimate the variance. I use that formula if you look back. And if I want to estimate the estimated variance of my estimator, it's the same, but the big S becomes a little s. Previous chapter. Now, what happens if, and I've given the values again, the formulas for big S and small s. Suppose I want to do it without replacement sampling, but also with stratification. So you're just going to divide it into groups, and then you're going to take simple random sampling without replacement from each group. How do we do that? It's very simple. You estimate the mean. What was it before? We used to have a Y bar. Now it's changed. You can't just add together the means. If I've got the average for the boys and the average for the girls, I can't average those two values. You've got to use what we call a weighted average. Okay? So you've got to multiply by the size because this will give you your total. If you've got the total, you divide by n and that's the mean. Okay? If you're 2, it's like you can't say a quarter plus a half. You've got to get your common denominator. That's exactly what that is doing. And similarly, the variance is given by this formula here. It's very similar to what we've done before. How would you take the variance there? 1 over n squared because of the independence. You can sum the variance of each nl squared, and you'll see this is just the variance of the previous one. And similarly, the estimated variance is exactly like before. The big S becomes a small s. Everything's the same, and the big S becomes a small s. So the next thing, make sure you can see why simple random sampling without replacement gives better results by stratifying if you're estimating the mean as well. We can see here, if you want the variance, you've got the S squared if you don't stratify. Now I'm estimating the mean. It's just like before. You look at the variance of the mean, not the total now. If you stratify, instead of this formula, you're going to use this one, which is very similar. Except now instead of an S squared, you've got an S squared L. So you put similar groups together, like all the old people with high blood pressure on one group and so on. So if we go back to our previous example, suppose we want to determine the average amount spent on groceries by a household of a particular geographical area. You know we said we're going to divide according to urban and rural. So in this particular case, you want to see, you're going to divide by urban and rural, and you would expect the urban people to be more similar in their spending and the rural people, so you'll get the S squared will be, S1 squared will be the variance here, S2 squared will be the variance there, and this would then be smaller than that value exactly because of that. So if we just from the whole set without stratifying, simple random sampling without replacement, estimating population mean, we take n from n, and we've got all the households together, and we know it's this formula where it's that S squared. Whereas if you're doing stratification and you're stratifying according to rural and urban, so now there are two groups, rural and urban, so I don't have H, I've got that previous formula, but now I've got this here with the S1 squared, S2 squared. This will be the variance amongst all the rural people and the variance amongst all the urban people. So the rural is here. This is the variance amongst the rural people to do with their household spending on groceries. So you'll have a sample just from the rural people, another sample just from the urban people, and why 1R, the family from the rural area, family R, what's his grocery bill for the month, and 2J will be from the urban area, and so on. And you can see because of this will be the variance of all the values from the rural area, and that is from the urban area. So this will definitely give you a smaller number than that. So stratification is as long as you've stratified according to something which puts people together that are similar. So you couldn't, for example, say I'm going to put people into groups for instead of urban and rural. I want to look at their household income, and I put depending on whether you're wearing a red shirt today or a blue shirt. It makes no sense. That won't help you to reduce your variance. So the next thing we're going to do, and I'll have you know, this is the last one. We're on slide 29 of 29. So thank you for bearing with me. I'm glad to do this quickly because I want to put it all into one video. What do we have? We want to estimate. We've estimated the population mean. We've estimated the population total. We've estimated the proportion belonging to a category. And we've done all that using simple random sampling without replacement, and we stratified. And then we compared to if we didn't stratify. Now again, it's exactly like before, but we're not using theta as t or theta as y bar. This is the last one. We're using theta as p, and we're going to compare, if you don't stratify, compare to if you do stratify. What is the difference? And here it is. You know what it means to stratify. So you want to estimate. If you don't stratify, how do you estimate your proportion? You just take the sample proportion. If you do stratify, guess what? You do it as well, but just as in the case of the mean. Remember, your proportion is just the mean. I showed you it's ones and zeros. It's exactly like that. You just do a weighted sum. Because really, you want to get the total. What is the proportion? It's like a mean. You want the total divided by n. But the total you get is by ny bar for each stratum. Okay? So there it is. The variance looks like that. And you did this before. This is chapter 2. Now we do exactly the same. But now you want to sum. Now, because of the independence, think of taking the variance of p hat. It's just the variance of this. Because of the independence, the sum of the variances, nh squared over n, variance of ph. This variance of pH looks exactly like this. Can you see? You can do it straight from here. If this is p hat, that is p, the variance of this looks like that from the previous chapter. So what would the variance here be? Variance p hat's variance here. So it will be, because of independence, I can sum the variances. Variance of this is the sum of the variances. This is nh over n. It's a constant squared. Variance of pH is just the variance of p for stratum h. But this is how one stratum behaves like this. You just put h's everywhere. Can you see? It's identical. It's this with h's everywhere. And then lastly, the estimated variance looks exactly the same as we look like that. And in the same way, it's just like that. But instead of big P's, you've got small p's. And that's the end of this. So thank you very much.